In today's lecture, we are going to discuss about algebra of continuous functions. We will discuss the theorems that can be exploited to generate many continuous functions, its proof and relating examples. In previous video, we have discussed about continuous functions, how a function becomes continuous at a point, discontinuous functions, different types of discontinuity like jump discontinuity, infinite discontinuity and point discontinuity. Now, you know what a continuous function means. So today we are talking about algebra of continuous function. By algebra, we means here general arithmetic operations like addition, subtraction, multiplication, division and so on. So algebra of continuous function deals with basic arithmetic operations performed with continuous functions. Theorem 1. Suppose f and g be two real functions continuous at x is equal to a, where a is a real number, then sum of these two functions is continuous at x is equal to a. The second rule is f minus g, that is the difference of two continuous functions, is continuous at x is equal to a. The third rule is f dot g, that is the product of two continuous functions, is continuous at x is equal to a. And the fourth one is f by g is continuous at x is equal to a, provided g of a is not equal to 0. Now, there are some special cases. Rule 5 is a special case of product rule. If f of x is a constant function, say some real number lambda, then lambda dot g is continuous at x is equal to a. And the sixth one is the special case of this quotient rule. If f of x is a constant function lambda, then lambda by g is continuous at x is equal to a, provided g of a is not equal to 0. So, this is our first theorem, and this theorem is very helpful to check whether certain functions are continuous or not. Now, we are going to check the continuity of this following functions. First, we are checking the continuity of the sum of two continuous functions at x is equal to a. We know for a function to be continuous at a point, there are certain conditions to be satisfied. Since f of x and g of x both are continuous functions, so they already satisfy the condition of continuity. That is, f of a and g of a are defined and limit of the function is equal to the value of the function. So it is clear that f plus g is defined at x is equal to a, because both f of a and g of a are defined at x is equal to a. Now we have limit of x tends to a, f plus g of x, this is equal to limit x tends to a, f of x plus g of x. By applying the summation rule that you have studied in algebra of limits section in previous year, the limit of the sum of two functions is the sum of the limit of the function. That is, this can be written as limit x tends to a of f of x plus limit x tends to a of g of x. We separated the limits. So this is equal to f of a plus g of a, because f and g are continuous functions. Therefore, limit of the function is equal to the value of the function. So this is equal to f of a plus g of a. So this can be written as f plus g of a. Hence, we get limit x tends to a, f plus g of x is equal to f plus g of a. That is, the limit of the function is equal to the value of the function. Hence, f plus g is continuous at x is equal to a. Hence, we prove that the sum of two continuous functions is continuous at x is equal to a. Now, in a similar way, we can do the subtraction rule. Proof 2. Check the continuity of f minus g at x is equal to a. We have limit x tends to a, f minus g of x is equal to limit x tends to a, f of x minus g of x. By the theorem on limits, the limit of the difference of two functions is the difference of the limit of the function. So this is equal to limit x tends to a of f of x minus limit x tends to a of g of x. We separated the limits. This is equal to, since f of x and g of x are continuous functions, so limit of the function is equal to the value of the function. So limit x tends to a, f of x is equal to f of a minus limit x tends to a, g of x is equal to g of a. This is equal to f minus g into a. Hence, limit x tends to a, f minus g of x is equal to f minus g into a. That is, the difference of two continuous functions is continuous at x is equal to a. Hence, f minus g is continuous at x is equal to a. Our third proof is check the continuity of f dot g at x is equal to a. We have limit x tends to a, f dot g of x. This is equal to limit x tends to a of f of x dot g of x. This is equal to, by the theorem on limits, the limit of the product of two functions is the product of the limit of the function. That is, limit x tends to a, f of x dot limit x tends to a, g of x by the theorem of limits. So this is equal to, since f of x and g of x both are continuous functions, so this can be written as limit x tends to a, f of x can be written as f of a dot limit x tends to a, g of x can be written as g of a. This is equal to f of a dot g of a can be written as f dot g into a. Therefore, limit x tends to a, f dot g of x is equal to f dot g into a. That is, the limit of the function is equal to the value of the function at that point. This f dot g is continuous at x is equal to a. Thus, we proved the product of two continuous functions is continuous at x is equal to a. Check the continuity of division of two continuous functions at x is equal to a. Limit x tends to a, f by g of x, this is equal to limit x tends to a, f of x by g of x. So this is equal to limit x tends to a, f of x divided by limit x tends to a, g of x by the theorem on limits. By the quotient rule, the limit of the quotient of two function is the quotient of the limits of the function. So this is equal to limit x tends to a f of x divided by limit x tends to a g of x. So this is equal to, since f of x and g of x both are continuous functions, so this is equal to limit x tends to a f of x is f of a divided by limit x tends to a g of x is g of a. Since f and g are continuous functions, so this is equal to f by g of a. Therefore, limit x tends to a f by g of x is equal to f by g of a. Limit of the function is equal to the value of the function at that point. Hence, f by g is continuous at x is equal to a. Hence, we prove that the quotient of two continuous functions is continuous at x is equal to a. Rule 5. Check the continuity of lambda dot g at x is equal to a. We know Rule 5 is a special case of Rule 3, that is the product rule, where f is a constant function which is lambda. We have limit x tends to a lambda dot g of x. This is equal to limit x tends to a lambda dot g of x. When limit goes inside, this becomes limit x tends to a lambda dot limit x tends to a g of x. By constant rule, limit of a constant is a constant, that is lambda, and here limit x tends to a g of x is g of a. So this is equal to lambda dot g of a, or this can be written as lambda dot g into a. Therefore, limit x tends to a lambda dot g of x is equal to lambda dot g into a. That is, limit of the function is equal to the value of the function. Hence, we prove that lambda dot g is a continuous function at x is equal to a. Rule 6. Check the continuity of lambda by g at x is equal to a. This is a special case of Rule 4, that is quotient rule, where f of x is equal to lambda. We have limit x tends to a lambda by g of x is equal to limit x tends to a lambda by g of x. When limit goes inside, this becomes limit x tends to a lambda by limit x tends to a g of x. This is equal to limit of a constant is constant, that is lambda, by limit x tends to a g of x is g of a. This can be written as lambda by g of a. Therefore, limit x tends to a lambda by g of x is equal to lambda by g into a. Hence, it proved that lambda by g is a continuous function at x is equal to a. Now, we can do some examples relating this theorem. Example 1. Discuss the continuity of sine function. Here, the function f of x is equal to sine x. So, limit x tends to c, f of x is equal to limit x tends to c sine x. Now put x is equal to c plus h. If x tends to c, then we know h tends to 0. Therefore, this can be written as limit sine of, instead of x, it is c plus h. So, limit sine c plus h as h tends to 0. We know sine a plus b is equal to sine a cos b plus cos a sine b. So, this is equal to limit h tends to 0. Now, expand this. So, sine c cos h plus cos c sine h. By rule 1 and 3, we can split and apply the limits. So, this is equal to limit h tends to 0 sine c cos h plus limit h tends to 0 cos c sine h. Now apply the limits. So this is equal to sine c into cos 0 plus cos c into sine 0. Now cos 0 is 1 and sine 0 is 0. So this is equal to sine c plus 0, which is sine c. This is equal to f of c. Therefore, our function limit x tends to c f of x is equal to f of c. Limit of the function is equal to the value of the function at that point. Hence, we proved sin x is a continuous function. In a similar way, we can do the cosine function. Example 2. Discuss the continuity of cosine function. Here, f of x is equal to cos x. Just limit x tends to c, f of x is equal to limit x tends to c cos x. Now, put x is equal to c plus h. If x tends to c, then h tends to 0. So, this is equal to limit h tends to 0 cos of c plus h. This is equal to limit h tends to 0 into cos c plus h is cos c cos h minus sin c sin h. This is equal to, now separated the limits. So limit h tends to 0 into cos c cos h minus limit h tends to 0 sin c sin h. This is equal to, now apply the limits. So cos c into cos 0 minus sin c into sin 0. Now what is cos 0? This is 1 and sin 0 is 0. So this is equal to cos c minus 0, which is cos c. This is equal to f of c. Therefore, limit x tends to c, f of x is equal to f of c. Hence, we proved cosine function is a continuous function. Example 3. Prove that the function defined by f of x is equal to tan x is a continuous function. Given f of x is equal to tan x, which is sin x by cos x. Here, the function f of x is defined for all real numbers except cos x is equal to 0, which means that x should not be equal to 2n plus 1 into pi by 2. Let P of x is equal to sin x and Q of x is equal to cos x. We have proved that sin x and cos x both are continuous functions for all real numbers. So this implies that P of x and Q of x is continuous functions. Both are continuous functions. Now, by algebra of continuous functions, if P of x and Q of x both are continuous functions, then f of x, being a quotient of two continuous functions, is also a continuous function for all real numbers such that Q of x is not equal to 0. This implies f of x is equal to sin x by cos x is continuous for all real numbers such that cos x is not equal to 0. Hence, tan x is continuous for all real numbers except x is equal to 2n plus 1 into pi by 2. Composition of functions. This refers to the combination of two or more functions in a manner where output of one function becomes the input of another function, and it is usually represented as f composed with g of x, which is equal to f of g of x. This notation tells you to start with the innermost function, that is g of x, then the second function f. That is, we are replacing x in f of x with g of x. For example, let f of x is equal to x plus 1 and g of x is equal to 2x. Now, f for g of x is equal to f of g of x. Now, what is g of x here? This is 2x. So, f of 2x, which is, we have f of x is x plus 1. So, f of 2x is 2x plus 1. Instead of x, we place 2x here. So, it becomes 2x plus 1. So, f of g of x is 2x plus 1. Always remember that f of g of x does not usually have the same value as g of f of x. In this problem, if we check g of f of x, this is equal to g of, now what is f of x? F of x is x plus 1. We have g of x is 2x. Therefore, g of x plus 1 is 2 into x plus 1, which is 2x plus 2. Here, f of g of x is not equal to g of f of x. So, order matters when calculating their composition. So, this is a brief introduction about composition of functions. Now, we are moving on to the second theorem, which shows the continuity of composition functions. Theorem 2. Let f and g be two real functions such that f for g is defined at x is equal to a. If g is continuous at a and f is continuous at g of a, then f for g is continuous at x is equal to a. So, we have two functions g and f, both are continuous functions. Given g is continuous at a, which means that limit x tends to a g of x, this is equal to g of a. Limit of the function is equal to the value of the function at that point. And f is continuous at g of a, that is limit x tends to g of a of f of x, this is equal to f of g of a. Now, we have to check f for g is continuous at x is equal to a. We have f composed with g of x is equal to f of g of x. If we apply the limit, this gives limit x tends to a f for g of x, this is equal to limit x tends to a f of g of x. This is equal to When limit goes inside, this becomes f into limit x tends to a g of x. Now limit x tends to a g of x is g of a. So this gives f into g of a. Where f of g of a is the limit of the function and it is a continuous function. So we can write limit x tends to a f of g of x is equal to f of g of a. Hence, it is proved that the composition of two continuous functions is continuous at a given point. Hence, f of g is continuous at x is equal to a. Now, let's do some examples. Example 1. Show that the function defined by f of x is equal to sin x square is a continuous function. Given f of x is equal to sin x square. Let g of x is equal to sin x and h of x is equal to x square. We have g of h of x is equal to g of h of x. This is equal to g of, what is h of x here? This is x square. So this becomes, we have g of x is equal to sin x. Therefore, g of x square is equal to sin of x square. Now, what is sin of x square? This is f of x. So this becomes f of x. So we can write f of x is equal to g of h of x. Here, g of x is sin x, where sin x is a continuous function that we have proved in the previous example. And h of x is x square and it is a polynomial function. We know polynomial function is a continuous function. If two functions are continuous, then by theorem 2, their composition is also a continuous function. So here g of h of x is a continuous function. Which means that f of x is a continuous function. Example 2. Prove that every rational number is continuous. We know every rational number is of the form p by q, where q is not equal to 0. Let f of x is equal to p of x by q of x, where p of x and q of x both are polynomial function and q of x is not equal to 0. We know every polynomial functions are continuous functions. Therefore, p of x and q of x are continuous functions. By algebra of continuous function, if p and q are continuous functions, then their ratio p by q is also a continuous function. So this implies f of x is equal to p of x by q of x is also a continuous function for all real numbers except q of x is not equal to 0. Example 3. Show that the function defined by f of x is equal to modulus of 1 minus x plus modulus x, where x is any real number, is a continuous function. Given f of x is equal to modulus of 1 minus x plus modulus x, let g of x is equal to 1 minus x plus modulus x and h of x is equal to modulus x. Then h of g of x which is h of g of x. This is equal to h of, now what is g of x here? This is 1 minus x plus modulus x. This is equal to, we have h of x is modulus x. Therefore, h of 1 minus x plus modulus x is modulus of 1 minus x plus modulus x. Instead of x, we have to put 1 minus x plus modulus x here. So, this becomes modulus of 1 minus x plus modulus x. So, this is equal to f of x. We know that modulus functions are continuous functions. Therefore, h of x is a continuous function. Because modulus functions are continuous functions, and g of x is the sum of 1 minus x plus modulus x, where 1 minus x is a polynomial function, and we know that polynomial function is a continuous function. So g of x is the sum of a polynomial function and modulus function, that is sum of two continuous functions. We know that by rule 1, sum of two continuous function is also a continuous function. Therefore, g of x is a continuous function. Hence, h of x and g of x both are continuous function. So, by algebra of continuous function, if two functions are continuous, then their composition is also a continuous function. Therefore, HOG of x is continuous function. Now, what is h of g of x? This is f of x. This implies that f of x is a continuous function.